Yeah. See here, in this circuit, uh, we again have a switch which uh, keeps switching between position 1 and position 2. And at t equal to 0, it is being switched from position 1 to position 2. Okay. Steady state has been reached with switch at position 1, as was the case in the last problem. Then how is this particular circuit different? See, the positions of the inductor and capacitor have been interchanged. Here in problem number 6, uh, very similar circuit, but here was the capacitor and here was the inductor. Now in the problem that we have taken today, these positions have been just interchanged. Understand that? And what is that they're asking? They're asking us the same. Okay, this is switch K. Okay, and it is being switched from 1 to 2 at t equal to 0. Steady state has been reached with switch at position 1. That means when this switch was at position 1, the steady state had reached. Okay, and in steady state, why they are giving us the information of steady state? Because we have to find out I of 0 plus. Okay, so to find out I of 0 plus, I need steady state conditions, because if I find out I of 0 minus, okay, I of 0 plus would also be same. I of 0 minus would be found out in steady state. The same current would continue at t equal to 0 plus also. So for that purpose, they've given us the steady state condition. Get that point? Once you find out I of 0 plus, we can get into what is the circuit at I t equal to 0 plus to find out the first order and second order differential. Everybody understand that? Okay, so let's go with the solution. Let's say all the things that we have understood from the problem statement. What is that? The circuit is at steady state, steady state uh, for t less than 0 with switch at position 1. P1 means it's position 1. I've told you why do we need this? To find out I of 0 plus. Okay, so to find I of 0 plus, what do we need to do? We need to find out I of 0 minus. So that means consider the circuit at t equal to 0 minus. Okay, so in that it is at steady state. Okay, and position 1, switch is at position 1. Can we write down the circuit now, everybody? Just write down this. I'll be writing down the circuit here. At steady state, what would happen? At steady state, what all you understand? At steady state, L is replaced by short circuit and C is replaced by open circuit. This is what we know at steady state. Okay, so that needs to be brought into act. Now we are very clearly told that the position should be at 1. Okay, the switch position should be at 1, so it is at 1. Okay, let's take this resistor, and what's happening to the capacitor? Capacitor is open circuited. Fine. Now this is position 1. At position 2 we have the inductor. Okay, so that inductor needs to be what? Inductor needs to be short circuited. So this is short circuited inductor, this is open circuited capacitor. Fine, so this is 20 ohms. Now what is flowing? What should be flowing at t equal to 0 plus? Sorry, t equal to t equal to 0 minus. What should be flowing? I of 0 minus has to be flowing. Understand? I of 0 minus has to be flowing. Now what should be there across this? There should be V of 0 minus. plus minus. What is V? This V is the voltage across the capacitor. This is the current that is flowing. This is the current that is flowing when the circuit was at steady state at t equal to 0 minus. Understand that? So from this, can we find out I of 0 minus and V of 0 minus is the question. Can we do that? Yeah. See here now. See here. There is a current flow, right? I of 0 minus is 0. Why we can say I of 0 minus is 0? Because it is open circuit. It is open circuit. Fine. What is V of 0 minus? The current is not flowing. Does that mean that this voltage would be 0? So we need to think of that. Okay. So let's see what happens with these two. Okay. Let's copy this. So this is the circuit we have considered at t equal to 0 minus, mind you, when the switch was at position 1. So this is how the things are going to look like. Okay. Now we can directly say that I of 0 minus is 0. Is that okay with you, everybody? I of 0 minus is 0. Fine. So since there is open circuit here, this implies that I of 0 minus is what? Is 0. Understand that? Now since I of 0 minus is 0, I of 0 plus is also going to be a 0. Understand that? Because when this switch comes to position 2, when this switch comes to position 2, okay, at t equal to 0 plus, the still same current would be flowing through the inductor. Everybody understand that? So as of now, you may mistake that I of 0 minus is not the current that is flowing through the inductor. See, inductor is here. Inductor is here. This is the capacitor. You may mistake that I of 0 minus is not the current that is flowing through the inductor at t equal to 0 minus. But see what happens at t equal to 0 plus. At t equal to 0 plus, this particular switch will get to position 2. So that means now the inductor would come into picture. Understand? So I of 0 minus at t equal to 0 minus would be the current flowing through the inductor at t equal to 0 plus. So in that sense, we can say that I of 0 plus would be equal to I of 0 minus, and that would be 0. Everybody understand that? Okay. So I'm again telling you, don't mistake that I of 0 minus is not the current that is flowing through the inductor. Okay, at t equal to 0 minus, yes, it looks like that. Okay, so this being 20 ohms, it looks like that. But see what happens at t equal to 0 plus. T equal to 0 plus means this inductor would come into picture. Okay, and when this inductor comes into picture, still the same current is flowing. Okay, so in that sense, we can consider this as the current flowing through the inductor. And since the current through the inductor does not change instantaneously, we can say I of 0 plus is equal to I of 0 minus. Is that okay with you, everybody? Now, once we have found out current at t equal to 0 plus, okay, we need to find out the first order differentials at t equal to 0 plus. So to find out first order and second order differentials at t equal to 0 plus, we need to consider the circuit at t equal to 0 plus. But for I at t equal to 0 plus, whatever is the current at t equal to 0 minus, that is sufficient. But for first order and second order differentials, we need to write the circuit at t equal to 0 plus. So what would happen at t equal to 0 plus? How would the circuit look like? How the circuit is going to look like? We need to look at that. Okay. So let's see how it looks like at t equal to 0 plus. Everybody look at this. Okay. At why we are doing this at t equal to 0 plus? We have to find out the first order and second order differentials. That's why we are finding. That's why we are considering this. Fine. So this is that. So this is position 1. This is position 2. Okay. Now at t equal to 0 plus, L needs to be considered L only. Okay. So at t equal to 0 plus, the position is at 2. The switch is at position 2. Capacitor, let's write it as capacitor only. This is how the circuit is going to look like. This is 20 ohms. This is 1 Henry, and this is 1 microfarad. Now what's flowing? What's flowing? I of 0 plus is flowing, which we already have found out in the last case. So this is how it is going to look like. Now, this 40 volts, what is there? It is of no use to us. Okay, so this is how things would look like. Fine. So let's consider this. I hope everybody understand this. So this is how it is going to look like now. Fine. At t equal to 0 plus. Everybody just at t equal to 0 plus, this is how it is going to look like. Fine. Now, can you give me the first order and second order differentials? Everybody. Can you try applying the KVL and see that? Everybody. Apply KVL now. Okay. So this part, this 40 volts, what is that? This is redundant, mind you. Okay. So this part is redundant. You will just be having this particular path into consideration. Okay. So KVL implies what? KVL implies 20 into I of 0 plus. Then what is voltage across the capacitor given by? What is voltage across the capacitor? Since capacitor stores the voltage, okay, voltage across the capacitor is, we can write this as, what is there across this? V of 0 plus is dropping across this. So we shall write this as V of 0 plus only to begin with. Okay. And one more, again, we forgot to say that this V of, what is this V of 0 minus? At 0 minus, I need V of 0 plus also here. So what is V of 0 plus? V of 0 plus is V of 0 minus. We didn't find out V of 0 minus in the previous case. We just found out I of 0 plus. So let's not forget to find out the voltage across capacitor also. Now, to find out the voltage across capacitor, what we can do? We can apply KVL to this particular path. Okay. So KVL implies what in this particular case? Everybody just look at this. In the previous case, KVL implies that it's minus 40. Okay. Plus, what is there I of 0 minus flowing? Is there I of 0 minus flowing? What is the voltage across this 20 ohms? So it's 20 into what? I of 0 minus, right? But I of 0 minus is 0. Everybody understand that? So it's 20 into 0 plus what? V of 0 minus. So what would this imply? This implies that V of 0 minus is actually 40 volts, which further implies that V of 0 plus is also equal to V of 0 minus, since the voltage across the capacitor does not change instantaneously. Everybody understand that? So, though they had not asked us to find out V of 0 plus, we are keeping this V of 0 plus with us so that it would help us in getting the voltage across capacitor at t equal to 0 plus. Everybody understand? So we have both I of 0 plus and V of 0 plus with us. I of 0 plus is 0, but V of 0 minus, see here, it's not 0. Everybody may think that the current is not flowing, so the voltage drop is not there. But this is connected with this circuit. Everybody understand that? So it's almost like this. Just everybody understand. how the circuit is. So that circuit would now look like this, plus minus. So this is how the circuit should look like, plus minus V of 0 minus. This is how the circuit is. Okay, but if you see, if you just apply the KVL, you will see that what you will see, if you apply KVL, you will see that it's minus 40 plus V of 0 minus is equal to 0, which implies that V of 0 minus is actually equal to 40 volt. So sometimes, though the current is not flowing, there would be a voltage drop across the open circuit terminals. Okay, so this is something that one needs to be little careful about. Everybody understand? So here we have V of 0 plus. Okay, so that V of 0 plus is also found out in the previous case itself. Everybody just take down this at t equal to 0 minus. At t equal to 0 minus, what's happening is this. Okay, so this, instead of writing it as the integral equation, let's take this as plus V of 0 plus, or we can further write it as, see here, it's 1 by C. Okay, integral 0 to t. Okay, what, I of 0 plus dt. This is, let's just write that as it is now, plus what is 1 Henry doing there. So you have to now write the voltage across this inductor also. What is voltage across the inductor given by? It is given by what, 1 Henry. It's given by, let me just write that, it's L into di of 0 plus divided by dt. Okay, algebraic sum of all these voltages should be 0. What is this? This is V of 0 plus. Everybody understand that? So call this equation as 1. This is equation number 1 for you. Fine. What happens further now? What happens? Okay. Substituting I of 0 plus equal to 0 and V of 0 plus equal to 40 volts implies what? It implies it's 20 into 0 plus whole of the second term is V of 0 plus, so that's 40 plus. What is L there? L is 1. Okay, so it's di of 0, 1 into di of 0 plus divided by dt. Is this okay with you? So what would be our the first order differential of the current I of 0 plus? Therefore, di of 0 plus divided by dt is actually equal to minus 40 amperes per second. Is it okay with you, everybody? So this is how it looks like. Now to find out the second order differential, what do? We differentiate one with respect to t. Okay, so everybody differentiate equation 1 with respect to t. Differentiating equation 1 with respect to t implies what? It's 20 into di of 0 plus divided by dt. Okay, plus 1 by c into I of 0 plus, after differentiating the second term in equation number 1 would reduce to this. Okay, plus L into d square I of 0 plus divided by dt square. So this is how the third term is going to look like. Now in this, what is I of 0 plus? I of 0 plus is 0. Okay, so this term goes 0. This term goes 0. So let's just write that. So this implies that we have 20 into minus 40 plus 0, because I of 0 plus is 0, plus L is 1 Henry's. So you have the double differential here. Is that okay with you, everybody? Therefore, what is double differential of I of 0 plus is this. Therefore, it implies that d square of I of 0 plus by dt is actually 800 amperes per second square. The first order differential is amperes per second because current divided by time. Here it is current divided by time square. Okay, the double differential, second order differential. That is why it looks like this. Yeah, see, in this problem they have given us an inductor, a resistor in series. There is a switch. In parallel with this switch you have a capacitor of half farads. Okay, and the symbol of this switch very clearly says that the switch is being opened at t equal to 0. The switch is being opened at t equal to 0. That means at t equal to 0 minus, the switch was closed, and the switch was closed for a long time. See, because the circuit is in steady state with switch closed. The circuit is in steady state with switch closed means the switch was closed for a long time. So at t equal to 0 minus, the switch is closed. Okay, and it was closed for a long time. That's why at t equal to 0 minus, the circuit is at steady state. What is that they're asking? They're asking us to determine the voltage across the switch. See, voltage across the switch they are saying. So this voltage across the switch. So this may confuse you because we know what to do to find out the current through the inductor, or what to do to find the voltage across the capacitor. But to confuse what they're doing, they're asking us to find out the voltage across the switch. Switch is here. Okay, so this voltage across the switch is as good as the voltage across the capacitor is what we need to understand by observation. So if you are good enough, you should be able to understand whatever they're asking us to find out, that is the voltage across the switch is actually the voltage across the capacitor only. Okay, so that is the catch one needs to have here. Get that point? Okay, and till now we were asked to find out the first order and second order differentials of current through the inductor. But for a change, what's happening? We are asked to find out the first order differential of the voltage. Can we have the first order differential of voltage by applying the KVL is the question we need to ask. Okay, so let's go ahead and see what is going to happen. Fine. So everybody, we understand how to find out VK. We are asked to find out VK of 0 plus. So to find out VK of 0 plus, I need to find out VK of 0 minus. So to find out VK of 0 minus, I need to consider the circuit at t equal to 0 minus. And at t equal to 0 minus, the circuit is at steady state. And at steady state, L is short circuit, C is open circuit. So let's do that first and then bother about the first order differential of Vk. Okay, so everybody in the solution, okay, at t equal to 0 minus, at t equal to 0 minus, the switch is closed and circuit is at steady state. The circuit is at steady state. Therefore, C is open circuit and L is short circuit. So this is for your reference. So now write down the circuit diagram at t equal to 0 minus when the circuit is at steady state. Therefore, at t equal to 0 minus, the circuit looks like this. Everybody just copy it down. You have the voltage source. You have the switch closed now. The switch is closed. Understand? And this is open circuit. Everybody understand this? This is open circuit. D. capacitor is open circuit. Fine. The inductor is short circuit. Then we have the resistor R. This is okay with you, everybody? So this is how the circuit is going to look like. Fine. So when this is open circuit, what is there across this? Vk of 0 minus is there. So let's say this is plus and this is minus. And what is flowing through this? I of 0 minus is flowing. Okay, through the inductor, mind you. So what is this R? This R is 1 ohm. So what can we find out from this? We can find out the current as well as we can find out the voltage. Understand this? Now it's very clear that this voltage across the capacitor is actually the voltage across a short circuit. What is voltage across short circuit? What is voltage across? Voltage across a short circuit is 0. If there is no resistor, the voltage drop is 0. Resistance is 0, the drop is 0. So in that sense, what would happen to this? This is 0 actually. So if you take this, you will understand. Okay, there will not be any voltage drop because there is no resistor. Fine. So it very clearly says that this implies that, okay, Vk of 0 minus is 0. Since zero resistance, since voltage across, let's write that. Yeah, since V across short circuit is 0. This is big, very short circuit. See, this is open circuit. This is short circuit. So Vk across open circuit is actually Vk across short circuit because they are in parallel. So in that sense, this is true. So this further implies that Vk of 0 plus is actually equal to Vk of 0 minus, and that's equal to 0 volts. So this is just by observation we can say. We don't have to apply anything to do that. Fine. Next what? Next what? We need to find out I of 0 minus. So apply KVL. KVL implies what? It implies minus 2 plus I of 0 minus into 1 equal to 0. So this implies that I of 0 minus is 2 amps. Okay. So this further implies what? So this further implies that I of 0 plus is equal to I of 0 minus, and that's equal to 2 amps. Is this okay with you, everybody? Now we're asked to find out what next. We're asked to find out the first order differential of Vk of 0 plus. See, d by dt of Vk at t equal to 0 plus. Now, where will you find out the first order differential of the voltage? Everybody just understand here what we need to do. Okay. So first write the circuit at t equal to 0 plus. At t equal to 0 plus, what's happening? How would the circuit look like? The switch is open. Switch is open. Understand that? So how would be the circuit looking like? The circuit would look like this. The switch is open. Across that you have the capacitor. Then you have the inductor and the resistor like this. Fine. So this is half farad. This is 2 volts and 1 Henry and 1 ohm. Okay. What we need? We need this first order differential of the voltage, and nowhere we can find out the first order differential except where, let's go to the table that we had seen here. Everybody see this table. Where can I find out from this table? You should see where can I find out the differential of a voltage. Where can I find out the differential of a voltage? See here, this is integral of a voltage. This is integer or integral of the current. This is different. This is first order differential of current. See, first order differential of voltage can only be found out by writing the current equation through the capacitor. Understand? So we need to write the current equation through the capacitor. So KVL will not help you there. So everybody should write the current across the capacitor. Everybody understand that? Sorry, current through the capacitor. To find dvk by dt, fine, write the current equation through C. What is that? That is what? I of 0 plus is what we are writing. What is flowing? I of 0 plus is flowing. Everybody understand? So I of 0 plus is flowing. So where will this I of 0 plus flow? See here. Everywhere the I of 0 plus is flowing. So what is that I of 0 plus now? That I of 0 plus is actually equal to its C into d Vk of 0 plus by dt. Understand that? So we have the first order differential. So this implies that dvk of 0 plus by dt is actually 1 by c into I of 0 plus. C is what? Half farad. So it's 1 by half. And what is I of 0 plus that we have found out in the previous step? It is 2. So therefore, what would this be? So therefore, we can write that dvk of 0 plus by dt is actually 4 what? Volts per second for a change. 4 volts per second. So not everywhere the KVL would help, as was the case in the previous problems. In this problem, for a change, the voltage across the capacitor is asked, first order differential of voltage across the capacitor. So you need to see which equation would give you voltage across the capacitor differential, first order differential of voltage across the capacitor. Okay.